Along with the development of drones and electric vehicles, aircrafts that are safe, that is completely carbon-free or electric, low cost, low noise, and viable for short distance trips have been the interest of many people for several years. In case you are one of the many people wondering, how soon can we expect to see batteries that can power electric aircrafts? A Californian-based company focused on silicon anode development for high-energy density lithium-ion batteries has given us a hint. Amprius has obtained third-party performance verification for its silicon anode battery that offers extremely high energy density in a lightweight package. The cell is able to record an extremely high energy density of 504 Wh per kilogram and a volumetric density of 1321 Wh per liters at room temperature. This is an incredible achievement for electrical vertical takeoff and landing or evtols because it could mean their range will be doubled and electric vehicles will be lighter and faster. Hello friends and welcome to the Electrochemist. Thank you for tuning in to the channel. On this channel we discuss all things battery development, including existing batteries, new and emerging battery systems, battery supply chain, battery production, and battery application. If this is something that interests you, please subscribe to this channel, smash the like button, and keep watching. The introduction of electric aircrafts and evtols received a lot of promise because helicopters used for short distances are known to be very expensive to operate and they have multiple points of failures which evtols won't have, thereby making them safer and less costly to maintain. Similar to electric vehicles, the range and weight of electric aircrafts are dictated by the battery. A common claim in the industry is that for batteries to power electric aircrafts, they must deliver energy densities of nothing less than 400 Wh per kilogram. This 400 Wh per kilogram was first reviewed by Uber Elevate's paper published in 2016. Battery industry leader Elon Musk also tweeted the same value in 2019, claiming it was based on his own calculations. 3 years later, a Nature Energy publication showed that batteries with an energy density of up to 800 Wh per kilogram will be capable of powering an airplane the size of an Airbus A320 or a Boeing 737 with 180 passengers over 1,000 kilometers. Now, the maximum energy density recorded by commercially viable lithium-ion batteries today is 250 to 270 Wh per kilogram, which means we still have a long way to go. Notice I said commercially available and not researched or published, because I know that there are several companies that have developed different battery chemistries with exceedingly high energy densities, such as lithium sulfur, lithium air, and solid-state batteries. But these options are not yet commercially viable. If you would like me to do a video on how the 400 Wh per kilogram requirement was determined and what is the battery technology that is best positioned to lead the way in electric aviation based on where we are today, please drop a comment in the comment section. Please like this video and subscribe as we continue. Current lithium-ion batteries can offer 400 to 500 kilometer trips with 5 to 19 passengers, which makes sense for evtols or e-taxis. But their weight is still a challenge because they are simply too heavy for long-range commutes, and their charging time is too slow to support the number of flights required, thereby rendering them unviable. Some high-profile evtols are using batteries that weigh 600 kg or more, which means that their range is restricted to between 100 km and 200 km. For context, batteries that weigh 200 kg can only provide a range of 500 km. That is with a hybrid electric power system. The commercially available battery technology with the highest energy density today is the NMC or NCA lithium-ion batteries, and their specific energy is 270 Wh per kilogram. This battery uses a graphite anode, and the battery packs made from these cells often weigh too much for evtols or electric planes, that is if you want to get the right amount of range. One possible way to significantly improve their energy density and decrease weight is by using silicon anode. Silicon has 10 times higher specific capacity than graphite and can hold more lithium in each mass. Silicon's ability to hold more lithium ions in each volume unlocks a greater variety of cell design options. This means it has enormous scope to make cells with a higher energy density, lighter weight, as well as smaller battery packs which are ideal for aviation. However, Using silicon anode brings with it several issues such as the swelling, which is caused by large volume changes during cycling. That is, it expands by 300% as it incorporates the lithium ions into its structure, and this leads to pulverization or destruction of the anode. It also suffers from delamination or detachment of the electrode from the current collector and experiences unstable SCI layer that contributes to its capacity loss during cycling. There are several approaches to resolving these issues, and this includes size control and nanomorphology design, carbon surface coating, alloying, and void space engineering. Many of these approaches come with their challenges, especially the cost of material engineering. Therefore, several companies and researchers have been working on ways to manufacture high-quality silicon anodes at scale. And one company that has been working on silicon anode development is Californian-based Amprius. Amprius operates a research and development laboratory in Fremont, California. It recently signed a letter of intent for a 774,000 square foot facility in Brighton, Colorado, that will provide up to 5 gigawatt hours of manufacturing capacity. Amprius recently verified the performance of its silicon anode battery cells with third-party Tesla mobile power solutions. The results show that the cell provides 504 watt-hours per kilogram and 1,321 watt-hours per liter. When cycled at room temperature, Amprius said the silicon anode cell is roughly half the weight and volume of conventional lithium-ion batteries, which makes them a viable alternative for applications in the rapidly growing electric aviation space, as well as in EVs. This innovation will ultimately revolutionize how high we fly, how far we travel, and how long we can use our devices, said John Bornstein, president of Amprius Labs. Another commendable feature of this battery design is that customers can adjust the specifications on the battery cell platform to meet their specific needs. This includes the option to increase energy content in a battery pack without increasing weight, reducing weight in applications that target a fixed energy content, or a combination of both features. Higher energy is important for longer run times, range, and endurance, while lighter packs increase energy efficiency. The battery cells are planned to be integrated with the elto Zephyr, a high-altitude platform station. The Solar Electric Communications aircraft offers persistent Earth observation with 18 cm ground sampling distance, near real-time video and imagery from the stratosphere, day and night. We look forward to taking advantage of Amprius' 500 watt-hour per kilogram cell to further develop the Zephyr's unrivaled stratospheric endurance capabilities, said Pierre-Antoine Auberg, Chief Technical Officer at elto HAPS, an Airbus subsidiary. Amprius is a valued current supplier with a great track record, and we're confident that its battery will deliver the capability we need. This is an interesting plan, and I look forward to the performance of this Amprius' silicon-based cell in the Zephyr, because lithium-sulfur batteries were also installed in the Zephyr, and it achieved the longest endurance flight for 14 days and 22 minutes and 8 seconds. So it will be interesting to see how long these silicon-based cells will go, considering the lithium-sulfur batteries were also 500 watt-hours per kilogram. Now, in my opinion, yes, I think this accomplishment by Amprius is a great one. However, the manufacturing process is a very specialized and costly one, so it is applicable to only a niche market segment with lower volume and high prices. The batteries are based on proprietary anode electrodes built with proprietary equipment to grow carbon filaments directly onto the copper current collector and coating with silicon. This is a very slow and very expensive and not compatible process with a large coating equipment in EV cell factories. In summary, I think silicon nanowires are great for using for this application, but production at EV cost is really critical. So that said, I think it's still a significant accomplishment, and I look forward to seeing Amprius plans to scale up production and commercialization. I would like to certainly know what you think on Amprius and electric aviation, so please drop us a comment in the comment section below. If you've enjoyed this video, please show your support by smashing the like button, sharing this video, and make sure to subscribe to this channel. I love you, I appreciate you, and I'll see you in the next video.